Hello, everyone. Thank you for attending today's webinar. We're really excited to have you all on board. Before we get started, just want to make sure everyone's able to hear me okay. If you do, could you just say a thumbs up or yes on the questions tab or in the chat window? Perfect. I see a few yeses. Perfect. All right, let's get going. So before we start today's webinar, I have a couple of small announcements to make. For most of you who are aware of this, if not, we have our user conference coming up. It's called H2O World. It's on the it's this December, coming up in less than a month, December 4th and 5th in Mountain View, California. We got over 50 speakers from a bunch of different companies like Capital One, PayPal, ADP, Amazon, and so on, NVIDIA. So it's going to be filled with talks about machine learning, deep learning, AI. Folks are going to talk about how AI is transforming their business. In addition, we're going to have our grandmasters, including Marius. So we'll have all of our grandmasters giving talks on how to win Kaggle, how to do data science better. We'll have a full day of hands-on as well. If you are users of H2O, you'll have H2O, sparkling water, and driverless AI hands-ons all available to get the best out of the product. So you definitely don't want to miss it. It's the once-in-a-year opportunity to come and meet the makers of H2O. And for today, we have a special going on. If you go ahead to the website, it's actually world.h2oworld.h2o.ai, or from the homepage, click on this link, you'll get here. And go ahead and use this promo code, H2O Webinar. That will give you a 50% off one day. Today, if you register today, you guys will get a 50% off on the tickets. And that's an amazing offer. So again, I encourage you all to go ahead and sign up and come and attend our conference. We'd love to have you there. Okay. Perfect. And one other thing I want to mention is if you are attended some of our other webinars on Driverless AI and are very interested in trying out the product is now available for general audience. So you can go to the website, come to our website at h2o.ai, click on this link, the Driverless AI link, or you can go to the URL directly, h2o.ai/driverless-ai. I'll repeat, h2o.ai/driverless-ai. And once you come to this page, scroll all the way down, you'll see this form. Fill this form out. Use your company's email address, and you'll get a link to download the product and a trial license. We'll issue you a 28-day trial license instantly. So if you want to follow along what Marius is saying, you might want to try that. Or after you finish the webinar, if you want to sign up for a trial license, go ahead and do it. Okay, with that, let's jump ahead to today's webinar. So our speaker today is Mario Michailidis. He is a research data scientist at H2O.ai. More famously, he is the former world #1 in Kaggle. He has a PhD from the University College in London, and has worked on a whole bunch of different use cases across multiple data sets. He's also popularly known as Casanova for creating Casanova, which is a free GUI for credit scoring data mining, made 100% by himself. He also is the creator of the StackNet modeling framework. And I'm going to, at this point, hand it over to Mario so that he can give a little bit more of an introduction of what he has done and take us through the webinar. Over to you, Marius.
Hello, everyone. You can see my screen. Thank you for the introduction, Vinod. Right. So is everybody able to see my screen okay? Hopefully that's a yes. So today I would like to show you how you can get competitive using driverless AI. As Vinod said, my name is Marius Michailidis. Although the introduction was really good about myself, I would like to tell you a few things more. My official title is competitive data scientist. And as the name connotes, I need to make certain that we create tools or machine learning tools and processes which achieve high accuracy. In other words, they're competitive. And how do we know they're competitive? Because we tested against the best out there, against the best data scientists, and ensure that it achieves top performance. My PhD is in ensemble methods, that I've done it in London at the UCL. And when we say ensemble methods, we mean how we combine many different machine learning models in order to get better predictions. And I have been competing a lot in Kaggle, where I achieved the top 1 spot against something like 500,000 members. Now, I don't know if you know what Kaggle is, but it is essentially a data science platform that, among other things, it organizes machine learning competitions where the people who solve them best get different prizes or ranking points. So it kind of have a league of its own. And at some point, I was able to get the first spot, so I achieved the most ranking points, which I think kind of shows you that I have been exposed to very competitive environments, and I know what competitive means. People may have seen different blogs or different videos or webinars about driverless. I would like to show you my view of how I see it from a competitive point of view. And it is essentially an AI that creates AI, to put it simply. So essentially, it's an AI that creates machine learning models, and given some input, it does its own machine learning processing and gives you some output. This input is, some data. Normally, they're represented as a spreadsheet type of data, tabular data set with different columns, categorical or numeric. You have a target variable, which may be, will someone default? 1, yes, 0, no. You have an objective which you try to maximize or minimize. For example, consider the misclassification error. So you try to get the smallest prediction error possible. And then, given some allocated resources and some time you want the model to run, some CPU or GPU processing power, you can get it to run. So you can get to combine all these elements into driverless. Then driverless does its own machine learning processes, and then it generates some outputs. The most common outputs you might be familiar with is predictions. Obviously, you can get predictions for some test data. For example, will someone default, yes or no? The other thing you can get is you can get some interpretability about your model. There's a very good webinar about this, which I really advise you to look at if you haven't. It's very good. But essentially, it helps you to find why your score has given the scores it has given, basically. So why certain customers, why certain cases have gotten the score they had. So it helps you to get more insight about this and understand your model better. The other thing you can get is, I think, it is essentially related to the first one, to the second one, about interpretability. You can get more insight about your customers, about your data, and I will show you later how you can do that. And the last thing is that, not only the last, but one important element is that you can also extract all the feature engineering that driverless has done and use it for anything you want, basically, either modeling or understand the data. What I would like to do today is, I know most people know that you can get predictions, but I want to show you that there is life after this. Driverless can empower you to get even better predictions. When it's finished, you can get the predictions, and the predictions will give you a good score, but there are ways where you can improve on top of that using all this knowledge, all these outputs, and this is what basically I would like to show you today. So how does driverless become competitive? It's not secret that the most important thing driverless does is feature engineering. So this process is quite exhaustive and based on hypothesis testing. So I will try this feature or this variable interaction. If it performs better against some validation data, then I keep it, else I'll try something else. This process is quite exhaustive and detailed in another webinar, and I don't want to spend more time. I advise you to watch it if you want. But I just wanted to basically highlight that this is the most important bit. However, we have other ways to also improve predictions apart from feature engineering. We use a model called Xgboost, which has been quite successful. It is based on gradient boosted trees, and it has won many machine learning challenges. And it is the core of driverless in terms of how we make predictions, supervised learning predictions. However, these models, not only that, it is a recent trend right now that most machine learning models, in order to achieve good performance, you need to find a good set of hyperparameters. So this process might be quite time consuming. So I would like to give you a bit more feedback about how we do this in order to get better predictions. We call that the hyperparameter tuning or just the tuning process. People have been asking about this, that's why I want to cover it. And the last element, I guess, that hasn't been discussed so far is that we do deploy some ensemble modeling in order to get better predictions. And when I say ensemble modeling, I mean we combine various Xgboost models after the feature engineering is done in order to give you better performance. So going through the how we tune this model, the Xgboost model, this is essentially many decision trees together, connected through a gradient boosted algorithm. And we have determined that one of the most important parameters is the maximum depth. But before I tell you about this, I should highlight that we try to keep this process at the minimum. So we don't try to do too much tuning. And that's because when we do the feature engineering, we don't need to have the best model possible. When we try to explore which features are the best, we don't need to spend so much time to find the best model possible. We re-examine this at the end of the process, but initially is how can we get some good, sensible results quickly in order to get the feature engineering process going on, and then we will revisit that later on. So what we do first is we have determined that this parameter called maximum depth, which shows how complex the trees in the ensemble need to be, it is quite important. It may lead to significantly different feature engineering. So we try to find the best value for this the moment you load your data. So the moment the data gets loaded into driverless, a cross-validation process starts where we try different maximum depth levels for the Xgboost models, and we keep the one that had the best performance in the validation data. Then we commence, once we have found this, we leave everything else as default and we commence the feature engineering process. But additionally, the other thing that we do is we put everything else as default. We use the best maximum depth we have found, but then we deploy a small learning rate and we allow big room for the algorithm to develop. So the algorithm can run for multiple iterations. And then we use early stopping, which is we have a validation data set, and the moment performance starts dropping for the validation data, then we stop the growing of the Xgboost algorithm. It is simple, but it works well and it can give us some good initial results while we can focus in the feature engineering process. So to put it simply, initially you load the data, we find the maximum depth, then we start the feature engineering process, which may last in multiple iterations. Every time we use a validation data set, and we start growing a new Xgboost model, and the moment we see performance starts dropping, starts decreasing or becoming worse, we stop, and then we use that model for final predictions. Once we finish the feature engineering process, then we revisit these parameters through Ensemble, which I will cover in the next slide. Hopefully that makes sense. So the way we do the ensembling is again in the same logic. So we try to get a good result, but simply without spending so much time. So after the feature engineering is completed, based on how much resources you have allocated, so how much time and accuracy you want driverless to have, then it may build up to 40 different machine learning models, Xgboost models, on top of these best features found through the feature engineering process. So these different Xgboost models may have different maximum depths, may have different tree growing policies, which this is tree specific, you can ignore this for now, or other parameters that control the depth, like how many leaves we should have in one tree. And then we just take a simple average of all these 40 models. It sounds simple, and we will include other methods in the future, like stacking. But for the meantime, this works quite well. It doesn't take that much time, and it almost gives you a free boost on top of what a single model would have given you with the best features found. I would like to demonstrate the impact of this ensembling process of these up to 40 models through an example. From a popular Kaggle competition. So there was one which was organized by BNP Paribas. It had around 3,000 teams. It was about 2 years ago. What was interesting about this competition is that it had a good data set, but so a good mix of numerical and categorical features, but they were all anonymized, so you didn't know what everything was. So you had to take a very machine learning approach of determining which features are useful. You couldn't understand, like from the features what they were. The data set was not very big, but not very small, and you had to predict, as this was an insurance type of competition, whether given these characteristics we should accelerate the approval of a claim or not. And you can see the usefulness of this. It can help allocate resources better. What's interesting is that driverless AI, after a few hours work in a CPU, can achieve a top 2%, which is really good. And what makes it really good is that it had taken my team almost 3 weeks to get to that score. We eventually finished third in that competition, so I know how demanding it was, and I can tell you this result is pretty good. It's pretty impressive. But I'd like to focus on the ensemble part. So this is what the output of driverless AI is when I run this competition. So you have this middle panel, the yellow panel, which displays many options available to you, which we will go through later on after driverless has finished its process. Then, if you are interested, you can see which features or features interactions were the best. But I would like you to focus on this point on this chart on the down left, where you can see the performance, the accuracy, the error of the model through time. These are the validation results, the internal validations results. Here we measure log loss, so the smaller it is, the better it is, means the smaller the error. And you can see that through time, through different feature engineering iteration, the error becomes smaller and smaller, which is good. I want you to focus on this thin vertical line at the very end, which you can see the performance drops improves quite drastically. So the error drops quite a lot, which is really good. This right there, which I highlighted, is the ensemble impact. Because as I said, at the end, when feature engineering is done, then multiple models are going to be built and averaged in order to give you the final score. And you can see that proportionally versus any other improvement you had over over the hours it was running, then you can see the actual impact of the ensemble is quite big. In order to demonstrate this, looking the actual results, using only the driverless AI prediction, you could get around position 60 out of 3,000, which is top 2%. If I hadn't used the ensemble, this up to 40 models in the end, I would have finished around top 4% without it. I approximate this. So you can see it is essentially a free boost you got in the end without wasting that much time. I think it was around 25 to 30 minutes more, and you know, and it can have a big impact depending on the problem. This was just, you know, I wanted to show you the impact of ensemble. Now I would like to go through you to another example, which I would like to demonstrate how we can use driverless AI, how driverless AI can empower us in order to make better predictions. So what happens when the predictions are done? What can we do next to improve our score? How can we use all this output driverless has given us in order to make better predictions? And I will do this through another popular Kaggle challenge. It was one hosted in Kaggle, but organized by Amazon 4 years ago. Back then it was quite popular. It has 1,700 teams approximately. This was a special competition to me because it was the first I ever participated. And I put a lot of time. I put around 3 to 4 weeks. And yeah, I really enjoyed it. It's an interesting competition because you don't have many columns, actually only 8 unique columns. But there is a lot of things you can do with them. You have to do a lot of feature engineering in order to get a good score because they're all categorical and they have very high cardinality. They're represented as numbers, but in reality they're categorical variables. And they have thousands of different unique values. So you need to work carefully to find a good mix of features that don't overfeed and generalize well to unseen data in order to get a good score. The dataset is not very big, but it is big enough to get significant results, and I think that makes it an interesting case. The scope was simple, a binary target. You had to predict if an employee would require special accesses. When we say accesses like administration rights, for example. If an employee has this job title and works in this department, will he need administrative rights? Yes or no? So it is a simple binary problem, and we use a metric called AUC, which we try to maximize. If you're not very familiar with it, just the highest this metric is, the highest, the better the discrimination between our score and the target variable. So if we have a high score, we would expect that people have higher probability to require special accesses and vice versa for a lower score. So a good value here is 1. That's a perfect. Not so good values around 0.5. This is what you need to know to process the following information. What the output of driverless AI is after running on 6 cores, after 2 hours, this is what it looks like. So you can see the performance in the validation data is around 0.9, but it will actually achieve better in the test leaderboard because driverless is actually quite conservative. It makes certain it doesn't overfit, and quite often you see better results in unobserved data. But you can see that the impact of ensemble is actually not so big here. If you look at iteration 100, you can see that it's a small vertical line that goes up. Here, higher is better. And the impact of ensemble is not so big here. Depends, it's different, it varies in different problems, but even that it's a useful information to know, that we couldn't get that much from this averaging at the end. So we need to explore different ways to improve our results. So once the model is finished, you can use the highlighted options which say score another dataset. In order to score another dataset, you can just drop a CSV file that has the same column names as the first one, and Driverless AI will do the scoring. Or you could have provided a test dataset in the beginning, and then Driverless will have the test predictions ready for you. Now, if you submit this to Kaggle after 2 hours of work, you get around position 80, which is around top 4.5%. What's really interesting about this is that when I first tried this competition, after 3 weeks or more of work, I didn't manage to beat it. It is quite sad in a way, but in my defense, I was in the beginning of this process, so I have improved a lot since then, hopefully. But it is a very impressive result. It's a demanding competition, and it was able to beat me in 2 hours. It took me 3 weeks. I studied a lot. I read the forums a lot, and I was not able to beat Driverless if we transfer 4 years back. But how we can improve our predictions further? If you remember that panel we had in the middle, which listed the different options you have available after the modeling is done, there is an option which is called download the holdout training predictions. These are essentially predictions for the training data. Why we're interested in that? Because since we have the target information available for the training data and all the features, we can see if there is any pattern there. We can see if our model misses certain cases. We can see if our model is not so good for some specific clusters of customers. So there are different things you could do. You can spot deficiencies or get other ideas. For example, you could plot the area under the rock cave and see if there are areas where there are different patterns. And you know, just here, there isn't that much to go on in respect to this, but it could have been. Besides, the score is quite high, but it is an option that you have. What I need to highlight here is that in order to ensure that we give you reliable training predictions estimates, we try to always make them look like test predictions. So we deploy a process which is called K cross validation, where this K is a hyperparameter. Here, for example, I put 4 in order to score the training data. I will explain to you how this process works. So assuming we have a training data set, here let's say we have 4 features, x0, x1, x2, x3, and the target variable, then we split it into 4 parts. Then we generate an empty vector, this spread vector on the right, in order to hold the training predictions. What we do then is we take a certain subset of the training data, let's say the red, the yellow, and the green part, and we make predictions for the blue part. So we built a model on the red, yellow, and green with the best features found in Driverless and the best parameters, and we make predictions for the blue part, and we save these predictions in the corresponding location in the training prediction vector. And then we try a different combination. We take the blue, the yellow, and the green part, we build the model, and then we make predictions to the red part, and we save these predictions in the corresponding location in the training vector. And we can essentially repeat this process. We can predict for the yellow data, the yellow part of the data, and also the green part of the data, and this is how we generate predictions for the whole training data in a holdout fashion. And in order to generate predictions for the test data, every time we were making predictions in these smaller parts of the training data, for example, only the green part, we were also making predictions at the same time for the test data. So for the test data, we have 4 predictions, and then we average those 4 predictions. And this is how we generate predictors for both training and test data. And the reason I spent so much time to explain this process is this is very closely related to another concept of ensembling called stacking. Because using the same methodology, we can create a new vector, so a new and empty prediction, and repeat the same process, repeat the same rotation, take a smaller part of the data, build a model, make predictions to another part of the data, save these predictions until we predict the whole training data, and then we make predictions for the test data. And this is how we can create multiple training predictions, which we can then combine, form a new data set, and use this data set for further modeling. So use these predictions as inputs to another model. And this is what we're going to do here. I just explained to you this process a bit so that you're familiar with the concept of stacking. By far my favorite option is driverless, is the one highlighted now. So once driverless has finished, I can download the transformed training and test data. So driverless commences an exhaustive feature engineering process, and after it finishes, you can ask to transform a training dataset or a test dataset that contains the same columns as given to driverless. It's a really, really good feature, because then you can use all these features to either build new models or get new ideas to add new features or understand your data better. So for this particular example, out of these 8 initial features, driverless generated, or 9, excuse me, it's basically 8 unique. It generated 55 new features in order to describe the target variable better. Another useful thing is that actually the target column will be available in the training dataset. So the moment it gets out, it's ready for remodeling. You can use all the new features and the target column to try different algorithms, for example. And this is what I did. But before that, let me just show you what's the impact of the feature engineering. So you had these initial features and 8 unique features. And you can see the AUC they had. That's because they're represented as numbers, but in reality they're categories. So that's why if you try to force them to be scores or predictions, they don't demonstrate a very predictive power towards with the target variable. So the way they are, if not transformed, are not really very useful because all AUC values are near 0.5, which means not very good discrimination with a target variable, almost non-existent. After driverless and we get this transformed dataset out, if we check the AUC of some of the top columns, there are some that achieve by themselves a very high AUC. The best feature had around 0.84 AUC. So you can see all this transformation is helping to make individual features really powerful. Another interesting point, here I'm just showing you the top ones, right? I mean, it's a long list of features. But another interesting point is that if you see the pattern of these features, they have this CV_TE or this WOE. The first one refers to target encoding through cross-validation. The other one refers to weight of evidence. So most of these type of features, they rely on information about the target variable. So you take averages or kind of average of the target variable to replace each one of the categories of these categorical features. That's a good way to do it because you don't increase the dimensionality of your data that much and you still get a good performance. However good it may be, it gives me ideas about other features that I could create. I can see that Driverless has done it. It has explored this area a lot, but there may be other areas where I can focus on, since it has already invested so much in here. So the first experiment that I did after I got this 80 position prediction is I extracted this transformed data out of Driverless and then I ran different machine learning models. And here I give you the results they got in terms of AUC in the test leaderboards. I tried different algorithms. I like this algorithm called LiveGBM, which is developed by Microsoft. The reason I tried this one is because Driverless uses Xgboost, so there was no need for me to do the same. So I tried different machine learning models here, and I generated predictions through this holdout training schema I explained before, and I also took this driverless AI holdout predictions and test predictions, and then I created a new data set. Then I used a new linear algorithm in order to fit on these predictions, which are now features, and I submitted that result on the test leaderboard. And the performance uplift was not really that much. So here you can see that out from position 80, I go to around position 73, which is nice because it is a free boost I got from just running more models. I didn't really do that much tuning. So I left the models almost with the default values. I only changed some objective functions. But using the same data out of driverless, just running more models and combining them was able to give me a better result. And it may not be that much, but it's still a small boost. Then I'm trying to think of different ways to improve my score. So I know that driverless is production ready. That means that it ignores information about the test data, because when you build the model, most of the times you don't have the test data available. You don't know it. You need to score. The future is unseen, is unknown. However, in competition, this doesn't happen. You most of the time have the test data available, you just don't know the answer. However, it is very useful to have this information available. And it is useful because the distribution in the test data might be different. You might have some features with some categories which are not present in the test data, which are in the training data, then you don't need to focus time on them. Also, there are some features you can create where you can leverage some information about the test data. For example, see how frequent a category is in the test data. You can create this kind of features because they can add value to your present models. And this is what I did, knowing that travelers will not try to, in a way, cheat and look onto the test data, but I know everybody, in a way, does in this kind of format. I just try to create a few more interactions of counts of features. So how many times a category or a combination of features appears in the test data. And what I did is I used exactly the same predictions as before, but I made a new model where, apart from the driverless AI transform data, I just included these counts of frequencies, all these counts of columns, of combinations of features in the test data. And this gave me a very sensible boost both in the training and the test leaderboard. And if I was to repeat the same stacking as before, so use a linear model to fit on those predictions, I was able to improve my score from position 73 to position 38 just by adding this information. So thinking a bit out of the box, thinking what driverless might have missed. In this scenario, I have to admit, it is a bit of cheating in a way. Irrespective of that, this is how you could think, how you could leverage your understanding of the data in order to get a better outcome. So using only driverless and that knowledge that I have, that it won't actually try to use the test data because it needs to be production ready, and creating a few features out of the test data set, I was able to improve my score even better. Now, if you see back on this slide, you can actually see that logistic regression, which is around in the middle, it doesn't perform as the rest of the models. Which it was a bit strange to me, because when I first participated in this competition, I remember this type of model was doing quite well for this particular challenge. So I know that driverless does the feature engineering based on three based models. So a linear model like logistic regression might not be a very good fit for these features. Therefore, I know that logistic regression can do really well with some dummy features. So with one-hot encoding, it helps capturing nonlinearity better. So using again this information of which features had done well in the past, if you remember these target encoding features, and past knowledge of logistic regression doing well with categorical data, if I use this sparse encoding, this dummy coding, I generated a few more interactions of features with this type of transformation. So you just use dummy variables, and I created a new model, which you can see it has the same features as everything else. So the same data as they come out from driverless, plus a few interactions of variables transformed with the dummy coding. And using this, I explore up to three-way interactions. So three ways you can combine variables. And I was able to improve performance of that particular model quite substantially. Now, if I was to repeat the same modeling process, so run a new model on the outputs of all these models, of all these predictions, exactly the same model, I would improve my score even further, and I would actually get in the test data around top 20. So I would get to top 1%. And I would like to show you the timeline of what I worked, which is just a small sample of what you could have done in order to improve your predictions. So the first 2 hours, driverless was basically working on itself. It generated all the features, and it achieved and around 79 rank, around top 4.5% in the leaderboard. Then in the next 2 hours after it finished, I took this data out, I prepared my pipeline of stacking, and I built various models, and I improved my score a little using stacking. I went to rank 73. Then in the next hour, I just use my knowledge of the fact that driverless would not try to see at the test data at all, and I try to leverage the fact that I knew the distribution in my test data in order to create smarter features, in order to create interactions of features and use frequency encoding to transform them. And this gave me an even bigger boost in the leaderboard. So it got me to top 2%. Then by seeing which models were not doing as well, and by looking which type of features driverless had built, which were mostly related to target encoding, I came up with the idea of also trying dummy coding to some of the features in order to improve results for the linear models, which were a bit left behind. And adding this model to my ensemble gave me an even further boost, put me to top 1% in that competition. And I think that's really nice, because within 6 hours, I was able to achieve this. So the first 2 hours, it was all driverless AI. The last 4 hours was all me thinking about how can I use this output and all this knowledge I have from driverless in order to get better predictions. And there are even more ways where you can improve your score. First of all, I terminated driverless after 2 hours of running. Theoretically, you can let it run a lot of time, and it will come up with slightly better results. Obviously, after a while, the performance uplift is not so big. But if you're really after accuracy, you can let it run quite a lot. I personally always try to stop it after 2-3 hours. The other thing you can do is you can, if you don't put a seed, if you don't put these options to reproduce results, every time driverless might come up with slightly different features. So you can run multiple driverless AI models and get the features, and every time they might be slightly different. That's because some of the interactions are generated through a genetic algorithm. So this is a different way where you can combine more dataset and more and build more models and get even better results through averaging or ensembling. The other thing you can do is you can get the predictions out, and then you can see where your model doesn't perform so well, or you can see which type of features were more dominant, and you can make adjustments. You can add some of your own ideas, or anyway, you can be creative in this area. For the meantime, for example, driverless doesn't include deep learning, but it will do in the future. But for the meantime, if there are any new algorithms, any other ideas you have, you can get the data out and try them, or you can add your own predictions, do your own, for example, stacking. And I want to close with a few things people have been asking me. So the first is, can driverless AI beat me in predictive modeling competitions? So after 4 years of intense modeling and have been ranked 1 in Kaggle, I would say if we compete against time, driverless AI will most probably beat me. So if we say, in the next day who can get the best score, I will most probably lose against driverless. If we compete for a longer time, let's say 2 or 3 weeks, I will most likely surpass it at some point. And you already see some of the limitations. For example, I could look at the test data. Driverless wouldn't look at the test data. So you can. I mean, there are ways for me to gain a lead, but still, I would say in the long run, I will most probably beat it. However, the main point I want to make is that as a data scientist, me personally, am I better if I use driverless AI? And the answer is definitely yes. And I have already shown you how this can happen. I can use all these extra features and add it into my model, or I can try to understand these features and see why they perform the way they are and get new ideas, for example. Or I could just take the predictions which are out of driverless and either apply them or combine them with other predictions, or do stacking as explained it before in order to improve predictions even further. I can use the interpretability module or other insight that there is out there in order to get more ideas, understand my model better, find any deficiencies. And something that I actually do most of the times is while I let driverless AI run, I can focus on other things. So I can do I can explore some visualizations or graphs or get some descriptives about the data. So I increase my understanding about the data set while driverless is doing its part. So when I get the predictions out and the training data and the features out, I'm already in a position to make some more strategic decisions about it. And that was about it. I mean, what I wanted to show you is how driverless AI can empower you. You can use all these features that happen after the prediction is done in order to move it further. As a data scientist, to use all this knowledge and capitalize on it and get even better results. That was about it. Thank you very much. I'm now happy to accept questions.
Perfect. Thank you, Marius.
Wonderful
webinar. This is Vinod here. All right, you got a bunch of good questions. I'm gonna pick a few, and then you can maybe answer those. And I think we got about 10 minutes, so let's see how many we can get through. Okay.
Yep.
So the first question is, what's the minimum data set size for driverless AI? Can it work on small data sets?
Well, I think that's a tough question in a way. I think it depends on the problem, but I would not. I would say you need at least 4,000 or 5,000 rows in order to start getting very reliable results. obviously, I think the ideal size is around like 100,000 rows. So after there, it's getting really consistent. You can see that even if you increase the data, normally you don't get that much uplift. But I would still say that you need at least 4,000 or 5,000 in order to allow it to get some good, in order to get sort of the best out of it.
Got it. Perfect.
And that's because it relies on a lot of cross validation, and it's good if those cross validation, these validation parts have at least an X size of 1,000 rows, for example. That any results, any feedback you get for the features you deployed, it is statistically significant.
Okay. Okay. The next question over here is, why do we have the AUC values for every feature? I think this is the slide you showed to compare if there is any signal in the data.
Yeah, I couldn't fit all 55 features there, so I put only the top performing ones. But yeah, we could have for all. You should know that there are even some with the negative relationship though. So it's not driverless that it will heavily look for a positive relationship. It might search for the opposite, a very negative relationship. But yeah, it was just a matter of fitting it into the screen, really. I thought I could already tell the story looking only at the top performing features.
So here's another question, interesting one. So the driverless performance came to about 0.9093, the AUC. You showed that logistic regression with one-hot encoding and the three-way feature interaction is about 0.908. So the question is, why should I use the driverless? Can I just use the logistic regression with one-hot encoding?
But it didn't use just the one-hot encoding, right? It also used the features from driverless. But yeah, no. But the result of driverless you saw in my screen, because I think driverless itself scored 909, right? So it performed, let me check. Yeah, so driverless scored 909 with the initial features, right? So logistic regression didn't top that even with the additional features, but it came close. But
I guess the question is whether you need stacking at that point, right? I think that's probably what the person is trying to ask.
Yeah, I mean, you could, you can get the features from driverless out and try your own models, right? You don't have to use the driverless AI predictions. As I said, the predictions will be as good as the feature engineering involved. So for me, the most important thing is actually the feature engineering. So assuming you can get it out, you can try your own models.
Got it. Perfect.
I'm not sure if that answers the question.
Yeah, that's good enough, I think. Here's another question. So the question is about, do we need to optimize the training data for driverless? Meaning, do they need to discretize it or group variables for high cardinality factors, etc., before we load it into driverless?
In principle, you don't need to do that. Actually, driverless is, look, any cleaning you do there, it helps, but driverless has its own ways of handling this. The only thing you might need to do at this point is just to make certain that you, for your numerical features that are actually categorical features, you make certain they have some sort of string inside. I think that's the only thing. So if you have a numerical feature which is actually categorical, make certain it looks categorical. So it has some sort of text inside, for example. I mean, that's the only thing. Otherwise, you don't really to do that much pre-processing. I mean, because driverless does its own pre-processing there. So it is quite good at handling this, at handling missing values. But theoretically, you can do it. It may add value.
Okay. Cool. Here's another question. It's an interesting one. How does driverless perform with data sets that have extremely imbalanced classes?
Yeah, I mean that's always a hard a hard problem to solve, right? I mean, you have so many when you have imbalanced classes. For the meantime, it makes certain that it optimizes, taking into account a weight feature. So you can adjust the weight of how important each row is, so you can sort of, in a way, control, in a way, oversampling or undersampling, or the importance of certain rows in the data if they are for X class. If this feature is not added yet, it will be added in the future. But you know, in general, there is not that much special treatment at the moment. So I would still advise you do some sort of pre-processing on this, on the data set you put in. For example, if you want to have a 50% representation of a binary class, better do it beforehand.
Got it. Here's a good question. I know you've been working on this. When will time series cross-validation be built into driverless?
We are building this now. So it will come out in one of the following versions. I mean, this is something we are working on. Cannot say exactly when, but it is being worked right now.
Here's another question. Can we get a list of all the candidate models that driverless builds at the end?
No, I don't think everything. Some of this information is in the log, but not everything is in. No, for the meantime, I don't think so. No, I mean, but this is something that could be added.
And do you have any plans? This is a question on when are deep learning libraries or models going to be added? Or are they, because you mentioned only Xgboost is used currently?
Yes, that's right. So Tensor, I've seen, yeah, Keras basically API on TensorFlow and standard multi-layer perceptor models is something that is already being worked on. But yeah, it has not been integrated yet. Okay. But yeah, standard multi-layer perception with perceptron, sorry, it is something we explore with Keras and TensorFlow backend.
Got it. Here's another question. Does driverless provide the code to create the features on an unseen data set?
Yes, so you can download the scoring, something called the scoring package. So after you finish, and some of the option is download the scoring package, which includes everything you need in order to transform the data. So you can see, actually, you can extract this part from the code. Perfect. So yeah, you can extract this part. It may be a little bit, it may take a while to figure it out, but you can.
Yeah, and we also have a Python client library, which also gives you an easy way to look at what's happening, right? So yeah, we can send you links to all of that after the webinar. Cool.
But yeah, everything is in the scoring package. I mean, it's not extremely easy to spot, but you can even see the models there related to the question you saw I was asked before.
Perfect. This is the last, I guess, final question. Someone says, I appreciate the ease of use with driverless. Is there a checklist for any gotchas? Is there something to be careful about while doing experiments in driverless?
Well, I just highlighted a few things. So it is the driverless will do a very good job in order to try exhaustively a lot of different hypothesis testing type of questions. But sometimes, in order you can use this time and knowledge of how it works in order to work in a way that adds value on top of that. For example, I just mentioned driverless doesn't know the test data. So if you are to score a data set which is significantly different in the future than now, you need to help driverless a bit to it. You know, you need to make certain, for example, that you construct your own validation data set, for example, where you try driverless, and that validation data set, it will be in the future, for example. This is something you need to be careful. Like you, I just briefly explained how driverless work. In order to make the most out of it, you also need to have in your mind that how to set up the experiment and model the experiment as best as you can. For example, and as I said, you know, if you give a training data set that contains X columns, but then you throw a test data set that has the same columns but randomized values, obviously it won't work well. So for the meantime, you are responsible in making certain that the test data look like the training data. This is something you need to look on. I have seen many people actually, in a way, not making good use of this. So building a model on training data and then providing some test data which are significantly different.
Perfect. All right, that brings us to the top of the hour. I want to thank everyone again for joining the webinar. I'm glad to mention.
May I quickly say that also 1.06 version of Driverless will be out soon, so you should you should try it out. A lot of improvements there.
Perfect, perfect. Yeah, it's coming out I think today or tomorrow. But if you go ahead and, as I said, go to the website and sign up for the trial. You'll get the link to the latest version and also a trial license. Thank you everyone for joining. Once again, if you are interested in H2O World, go ahead and sign up with the promo code H2O Webinar for 50% off. And I'll see you, most of you, in the next webinar. Thank you.